we'll be deriving the transfer function V2x over V1s for the given RC network. This problem is an application of classical control system analysis using Laplace transforms. The objective is to express the output voltage in terms of the input voltage in the S domain or the Laplace domain. To achieve this, we will convert the circuits into their impedance equivalents, determine the total impedance seen by the source, and then apply the voltage divider principle. By the end of this derivation, we will obtain a simplified transfer function that describes the dynamic behavior of the system. Thank you.
Hello, my name is Gia Samuel, and I'll be presenting on the circuit description of our work. So if we take a look at our circuit, we have an input voltage which is denoted by V1S, and connected to this input voltage is a resistor. This resistor is connected in series with a capacitor. Moving forward, we have our output node. For our output node, a resistor is connected in parallel with a capacitor. The output of this circuit, which is the output voltage of this circuit, which is V2S, is taken across this parallel combination. So essentially, we have a series impedance feeding a parallel impedance.
Okay, my name is Hadassah Adams, and for us to better understand the circuit to which we are deriving the transfer function, we have to draw it. So at the input node, the first resistor is connected to a capacitor in series. And at the output node, the second resistor is connected to the second capacitor in a parallel format. Okay, so this is the circuit which we are deriving the transfer function from. So a circuit description V1 is applied at the input terminal, and then the resistor is followed by the capacitor in series. At the output node, the R and C are in parallel across the output node to give us the transfer function. So my next colleague will try and understand how to calculate the voltage both in parallel and in series. So please, I must say, you understand many sums. And now I'll be explaining to you how we are going to calculate the resistances and then the impedance of the capacitor. So first of all, we would have to change it from the time domain to the frequency domain. This is because calculating in the time domain becomes very difficult when calculating the impedance of the capacitor and of an inductor. Because in the time domain, I of t is equal to c times change in the v over dt, which brings in a differentiation. So hence we have to convert into the Laplace domain in order to make calculations easier. So because of that, the impedance of a resistor remains R in the S domain. The impedance of a capacitor becomes 1 over SC, and then the impedance of an inductor becomes SL. Thank you.
Okay, so I'm in the person of the champion Emanuela Adakwa, and I'll be taking us through the series impedance. So we have the resistor which is in series with the capacitor, and in order to find that the total impedance, we have to add them. So we have R plus 1 on SC, which is in the Laplace domain, and then finding LCM, we have the SC as the LCM, R SC plus 1. So this is the total series impedance. Thank you.
So I'm in a person of triple two, and then I'll be talking about the parallel connection between the resistor and the capacitor. So from the diagram, you could see that the parallel connection happens like this. Sorry. So this is the connection for the parallel. Sorry. So this is the connection, the parallel aspect. So if we want to measure the impedance across the resistor and the capacitor, we have the parallel impedance to be ZP equal V1 times V2, which is the impedance across the capacitor over Z1. So my friend will continue from here to explain them in the Laplace domain.
I'm in the question of Isaac Toure, and I will be continuing on the expression for CP, which is the total impedance across the parallel connection of the resistor and the capacitor. So we assume the impedance across the resistor was Z1, and in Laplace domain, this is represented as R. And we assume the impedance across the capacitor is Z2, and in Laplace domain, this is represented as 1 on SC. So we said ZP was equal to the product of the two, which is Z1, Z2 on Z1 plus Z2. So now ZP is equal to, putting this into the expression, is equal to R on SC divided by R plus 1 on SC. So therefore ZP is equal to R on SC multiplying SC on 1 plus its RC. Therefore, ZP will be equal to R on 1 plus SRC.
My name is Melinda. I'm going to apply the voltage divider rule. We apply the voltage divider rule to relate the output voltage to the input voltage. In this circuit, the total impedance divider rule. We apply the voltage divider rule to relate the output voltage to the input voltage. In this circuit, the total impedance seen by the source is made up of two parts, which is the series impedance and the parallel impedance. Now, because the output voltage is also taken across the parallel branch, we treat that branch as the output portion of the divider. So the voltage divider will become V2 is equal to the parallel impedance of the series of the addition of the series impedance plus the parallel. This means that the output voltage depends on the total impedance contributed by the parallel section. So if the parallel section is large compared to the series part, more voltage appears at the output, and if it's small, less voltage appears at the output.
Okay, so hi, I'm Tuying someone, a member of the team, and I'm I'm here to talk about the transfer function. So using the voltage divider rule, we realize that our transfer function V2 is divided by V1 of S is equal to our total impedance on the parallel side divided by the total impedance on both the parallel and the series side. So ZS from my earlier colleague's presentation, realize that ZS is equal to R plus 1 on SC and ZP is equal to R on 1 plus SLC. Okay, so there's sorry. From our earlier term, we realize ZP is equal to R over S plus 1. Then our total group will be equal to our ZS, sorry, that is R plus 1 over ZS plus our value for our SRC, that is our value for the ZP, that is R over SRC plus 1. So after using our algebra and everything, we can have our V1 to be equal to SRC plus 1 whole squared plus SRC. When we simplify this one, we will get S squared R squared C squared plus 3SRC plus 1. Here, so if this is our value for our V1, our total transfer function, sorry, V1 applied not to place, should be equal to our R. When we use LCM to solve for our ZP, we have R on S, C plus 1, all on S squared R squared C squared plus 3S RC plus 1. Okay, so after that, using further simplification, we realize that our V naught over V1 of S should be equal to S R's all over S R S squared R squared C squared plus 3 C plus 1. So this is the total, our transfer function after we've been able to input the values for the various inputs. Thank you.
Alright, so from our final transfer function, we realize that we have the formula V of S, and we have all V equal to X squared R to C squared. We realize that we have a denominator which contains an x to the power 2 term. So this clearly means that we have a second order system here. Also, you have to know that to be able to really understand the dynamic behavior, it depends on the value of the R and C that we have. So with this, we can clearly conclude that the transfer function is describing how the system responds to different frequencies and inputs, right? And based on that, you can derive the transfer function using the impedance analysis, what we've learned in practical control systems, using the principles.